Okay. Okay. Ashok, I don't see.
Yeah, I'm here. Yeah, I'm here.
Yeah. No, the slides.
Oh, slides. Okay, I'll share it. Just 1 minute.
Yes, thanks.
Is this visible now?
Yeah, that's great. Thank you.
Thank you.
Okay, so welcome back to this next part of the talks. We will now have 2 talks, 30 minutes each, plus 10 minutes of questions. So now we will start with Sen from Harishchandra with classical soft graviton theorem. Take it away, Ashok.
Okay, thank you very much. So first of all, I'd like to thank the organizers for inviting me. I should also apologize that this will be a talk on more or less classical gravity. Even though near the end, I'll discuss some relation to soft theorem. In fact, that's the way we arrived at the results in the first place. Okay. But the talk will be mainly on classical gravity. Okay. So here is a brief plan. Okay, so the half of the talk will be basically in summarizing the results. Then I'll describe how we give a classical derivation. Okay, these are results in classical gravity, and they have fully classical derivation. But as I said, we originally arrived at these results from soft theorem, so I'll discuss the relation to soft theorem at the end. So let me then begin with the results. So we'll be considering a classical scattering, and we'll consider a general case where a set of objects with some asymptotic 4 momenta, P1 prime to Pm prime, they come together, then they interact via complicated forces, and then they disperse as a set of other objects with asymptotic 4 momenta P1 to Pn. Okay, we make no assumption about the number of particles, number of objects, or their momenta. Okay, of course, that's conservation. This also includes explosion, okay, where one object breaks up into many objects, okay, like for example, the explosion of a supernova. So these are the conditions, the mass shell conditions, and we'll be using mostly plus signature metric. And we'll choose the origin of space-time to be in the region where the scattering event takes place. Okay, the details will not be important, okay, but it's somewhere in that region. And you'll imagine that you have a detector D that's placed far away, okay, at Sky plus, and it detects a gravitational wave reaching it at some time, okay, T naught. So T naught will be given by the leading term will be R over C, okay, that's the normal light travel time, but then there are logarithmic corrections that come from the gravitational drag due to on the gravitational radiation. And again, we will not need to really know what these corrections are. So we'll define retarded time at the detector, okay, which is this U. So the gravitational wave is passing the detector around U equal to 0. And we'll be focusing on the late and early time tail of the radiation, which basically means that we'll be focusing on the value of the gravitational waveform at the detector at large positive U and large negative. Now it turns out that instead of working with H mu nu, it's more useful to work with this trace reverse metric E mu nu, which is defined here. Okay. But of course, it contains exactly the same information as H mu nu because we can recover H mu nu from E mu. And what the main results that we'll be discussing is that up to gauge transformation and corrections of order R to the -2, okay, which we don't care about, these are radiative fields. The E mu nu in the future, okay, and in the far future, we'll have an expansion of this form with coefficients A mu nu, B mu nu, F mu nu, etc. And in the far past, we'll have an expansion of this kind. Okay. And here I have chosen the convention where E mu nu goes to 0 in the far past, which means that we are assuming that the metric is flat metric in that's eta mu nu in the far past. Okay, we have chosen our coordinate system that. And the main point that I want to emphasize here is that these coefficients turn out to be universal in the sense that they are given solely by the momenta of the ingoing and outgoing objects, and they do not require any knowledge of the details of the scattering process. And in the next 2 slides, I'll give the expression for these coefficients in terms of the momenta of the ingoing and outgoing objects. So here are the expressions for these three coefficients, A mu nu, B mu nu, and C mu nu. Let me remind you that A mu nu and B mu nu are for the future. This is for the past. A mu nu is the constant part. This is the leading 1 over U piece. Okay, this is a leading correction for large U. And the important point to notice is, as I said, that the data that we need are only the initial and the final momenta. And of course, you need to know the direction of the detector related to the initial and the final momenta. So N captures the direction of the detector, and R, as I already said, is the distance to the detector. Otherwise, the details of these formula will not be important. Okay, it's just to show that it's possible to write down an explicit formula for these coefficients. And here are the expressions for F mu nu and G mu nu, okay, which are the sub-subleading terms. And again, the details are not important, but the important point is that they need exactly the same data, okay, namely the momenta of the ingoing and outgoing objects. So what I'll do in the next few slides is to describe some particular properties of this formula, okay, of these coefficients. So here are these formulae again. Now, A mu nu here is what is normally called the memory term, okay, because what this tells us is that there is a permanent change in the state of the detector after the passage of the gravitational wave, okay, that causes a permanent shift in the direction, the separation between the arms of the interferometer, for example. This is the memory effect, and this is related to the readings of graviton theorem, as was emphasized by Strominger quite some time ago. And these terms, okay, the subleading and the sub-subleading terms, are what I call tail terms. And these are related to logarithmic terms in the subleading and sub-subleading of graviton theorems. Okay, and this connection I'll discuss at the end of the talk. That will be the third part of these lectures. But again, let me emphasize that these formulae are purely classical formulae. Okay, we are considering classical gravitational scattering. So this is what I have emphasized here, that the result is a statement in classical GR, even though it was originally suggested by quantum soft graviton theorem. These also I have already said. And the third point is that this formula is not quite valid for when there are charged particles in the initial and the final states, okay, because there is long-range electromagnetic interaction between these charged particles, but there are known corrections to this formula if the initial and the final states contain charged particles. Okay, so the formula will look more complicated, and that's why I have not written them down explicitly. Now, as you notice that in the expressions for these coefficients that I wrote down, okay, particularly the final state coefficients, A mu nu, B mu nu, and F mu nu. So let me show again. So let's look at the A mu nu and B mu nu. You would see that A mu nu and B mu nu contains information both about the ingoing, these are the incoming momenta, and the outgoing momenta. Okay. C, on the other hand, contains information only about the incoming momenta, okay, the P primes. Now these outgoing momenta, okay, this sum over outgoing momenta, okay, in principle must include sum over also hard gravitational radiation, okay, because it really includes sum over all final states, which basically makes life a little complicated, because this says that the sum over final state particles should include integration over the outgoing flux of radiation, which you can regard as the flux of massless particles. So you have to really compute the full gravitational wave emission before you can compute these coefficients. And for A mu nu, okay, this is what is called the nonlinear memory term. That A mu nu receives contribution not just from the final state massive particles, but also from final state gravitational radiation. Now it turns out that there is a miraculous cancellation, and because of this miraculous cancellation, in B mu nu and F mu nu, the contribution from the massless final states can be expressed in terms of the massive state moment. So you do not really need to know what kind of gravitational radiation was emitted during this process, as long as you know what the final massive state moment are. And this makes it much easier to calculate this, because you do not need to find the gravitational wave spectrum emitted during the scattering. And I'll now describe exactly what you need to do to compute B mu nu and F mu nu, the formula that you need to use where you do not need information about the mass or the massless final state particles. So here is the basic result. It turns out, and let me emphasize at the beginning that these formulae that I'm showing here are not new formulae, but these just follow from manipulating the results already shown. You just have to set some of the particles to be massless and see and manipulate the formula. But the net upshot is that in B mu nu, we can drop the massless particles or radiation contribution in the sum of our final states, and instead add this quantity, where Pi is the total incoming momentum and Pf is the total outgoing momentum carried by massive particles. So the only information about massless particles that we need is the total momentum, that is the momentum that they carry away, and that is encoded in this Pf, because by momentum conservation, Pf is Pi minus the total amount of momentum carried away by massless particles. Similarly, F mu nu, the prescription is that we drop massless particles and radiation contribution from the sum of our final states and add this term over here. So even though these are not new formulae, these replacements makes it much easier to compute these quantities. And we'll see some specific features of this observation. So here is a further result, and this again more or less follows from what I said in the previous slide, that if the final state has at most one massive object, and it can have arbitrary number of massless objects or massless particles, then it turns out that these coefficients B mu nu and F mu nu become totally independent of the final state moment. And this has somewhat unusual consequences. So let me explain what the consequences. So let's imagine that we have a pair of massless or ultra-relativistic particles which pass each other at large impact parameter. If the impact parameter is large, then they more or less don't scatter. Okay, maybe there is little deflection, but they more or less go straight. But nevertheless, there is some gravitational wave that is emitted during this scattering, because after they have passed, at late time, they still feel long-range gravitational attraction of each other, and then this long-range gravitational pull make them accelerate or decelerate appropriately, and that causes them to emit some gravitational radiation. So a far-away detector will detect some gravitational wave profile due to the late time acceleration of these particles under each other's gravitational field. Now let's suppose we reduce the impact parameter. If we reduce the impact parameter, of course they will scatter gravitationally. In fact, they will bend. Right? If as you start reducing the impact parameter, they will bend under each other's gravitational force. But from what we saw in the last slide, because the final state, these coefficients B mu nu and F mu nu do not depend on the final state momentum, the fact that they actually bend, these particles actually bend during this process and the final state has changed, makes no difference to the late time gravitational profile that the detector detects. So as far as the detector is concerned, at late time, it feels as if the particles have just passed each other without any scattering. So this is what I have said, except for the memory term, the late time gravitational wave profile detected at the far away detector will remain unchanged because it's insensitive to the final moment. Now let's imagine that we reduce the impact parameter even further. And for sufficiently small impact parameter, these particles will collide, and they will coalesce to form a black hole. And in that process, of course, they will emit gravitational radiation. So the final state will be a black hole together with massless radiation. But nevertheless, the late time gravitational wave profile of the far away detector will remain unchanged, as if nothing has happened. And again, this follows from what I already said, because the final state contains one massive object and massless objects. And that means that the late time gravitational wave profile of the detector will be insensitive to this fact that there's one massive object in the final state. It will be the same as if the particles just passed through each other without scattering. In fact, the same argument tells us that this 1 over u and log u over u square tails vanish for binary black hole merger, because this process can be, this binary black hole merger can be thought of as one object, which is the original bound system, goes into one object plus gravitational radiation. And this is equivalent to one object going to one object, because the final state, massless particles don't matter. So one object going to one object plus gravitational radiation is the same as one object going to one object, because this should be insensitive to the final state. And of course, if there is just one object going to one object, then there is no gravitational radiation, which means this feature, of course, is valid only for B mu nu and F mu nu. So as far as B mu nu and F mu nu goes, they will be as if nothing has happened, which means that there will be no B mu nu or F mu nu in the final state. So 1 over u and log u over u square coefficients will vanish. Now, so far in our formula, there is no spin dependence. And this is expected to arise at order u to the minus 2. And some progress in this direction was made in this paper. But I'll not try to describe it here. Now, after we take Fourier transform of these results and go to frequency space, the results that I gave also give power spectrum of soft gravitational radiation. So here is an example. Again, consider the set of massless particle scattering at large impact parameter. And it turns out that the power spectrum of soft gravitational radiation for the scattering of a pair of massless particles at large impact parameter is given by a formula like this. This follows from the expressions for F mu nu and B mu nu and A mu nu that I wrote down. So here E is the energy of each particle. This is in the center of mass flame. Theta S is the deflection angle. So you see that more or less the up to the omega square log omega square term, you can determine what the power spectrum will be. And this in fact confirms an earlier conjecture by these authors on the sign of the second term. This is important because the sign of the second term means that the power spectrum actually starts growing as you go away from omega equal to 0. And eventually, of course, it will fall once omega becomes sufficiently large. So this means that the peak of the power spectrum happens at a non-zero frequency. So this was conjectured by these authors, and indeed the sign here confirms that conjecture, although the coefficient that we find is twice what the conjecture. Now let me go through the derivation. So first, as I said, I'll give the classical derivation and then I'll say how we arrived at these results from the soft theorem. So here is the general scattering process. I have only shown 4 external objects, but of course that's not necessary. And the idea is that we divide the space-time into the scattering region where non-trivial interaction takes place, and the asymptotic region where the particles interact by long-range gravitational force. And as I said, if they are charged particles, they will also interact by electromagnetic force. Then we iteratively solve the coupled equations of matter and gravity in the asymptotic region. And in this process, the matter equations, in fact, are evolved forward for incoming particles and backward for outgoing particles. This is, in fact, the main difference from what we normally do in a time evolution problem. And the reason that the matter equations are evolved backward for outgoing particles is because we are assuming that the final state data for final momenta are known. Because you want to express everything in terms of final momenta. And this makes all the difference in the analysis. The fact that you are allowed to evolve the matter equation starting from the final state. For incoming states, of course, we evolve them forward. Gravitational equations are always evolved forwards using retarded Green's function. That's the basic principle of how we proceed. So here are some technical details. So you split the metric into the flat background and the fluctuation. These are the trace reverse. This is the trace reverse metric that I already introduced. And then we rewrite the A.Sen's equation in the redundant gauge in this form. Of course, this looks very simple, but all the subtleties are in T mu nu. So T mu nu is the sum of the matter and the gravitational energy momentum tensor. And basically, all the nonlinear terms in H mu nu are included in TH mu nu. So anything that is not of this form, we include on the other side. And then once you have written it in this form, we raise all the indices, raise and lower all the indices by the flat metric. And I'll also set C equal to 1 from now on, just for to avoid some factors of C. And I should emphasize that we are not assuming weak gravity at this stage. Okay, even though I have written the metric as a sum of flat background plus H mu. You're not assuming necessarily that H mu is small at this stage. So this equation can be solved in quotes, okay, by using the retarded Green's function. But of course, this is not a solution because T mu nu involves E mu nu, right? So this is a coupled equation. Nevertheless, once you have written it in this form, okay, we can study the behavior of E mu nu for large x, okay, large mod x, large distance, because that's what we are interested in. Okay. And using explicit form, the retarded Green's function, one finds that at large distance, okay, E mu nu, okay, this is the Fourier transform of E mu nu. So there are two types of Fourier transforms involved here. One is just the time Fourier transform, that's what tilde means. Okay, so E tilde mu nu is a time Fourier transform. And hat means the full Fourier transform in the full space time. So one can show that this equation can be rewritten in this form, okay, where the time Fourier transform of E mu nu is related to the full Fourier transform of the energy momentum tensor. And here the K, of course, is related. I mean, you have to specify what K is, the argument K is in terms of this, and that's given here. Okay, so part of K, the direction of K is fixed by the direction of X. And here is one important point, that in terms of E tilde, what we find is that the memory term, the U inverse term and the U inverse log U term that we are after, they arise from 1 over omega, log omega, and omega log omega square term in T hat. Now, what is special about these terms is that these terms are all non-analytic in omega, which basically means that if you take sufficient number of derivatives with respect to omega, and then take the omega goes to 0 limit, these terms diverge. And that's what will make it easier to identify which terms we should keep and which terms we can throw away in the approximation that we are going to make now. So here is the basic principle, that we divide the integration region over X into two parts that I have already said. So the scattering region is some region of large size L around X equal to 0, where the scattering is taking place, and the asymptotic region is a complement of S. And the point is that because our goal is to compute terms in T hat that are non-analytic and as omega goes to 0, we can ignore the contribution from the finite region X in this integral. Because as long as this integral is running over a finite region, then however many term derivative with respect to omega you take, right? As you take derivatives with respect to omega, we bring more and more powers of X. But that will never diverge as long as the integration is running over a finite region. Okay, it will diverge only from the large X region. So this means that in this integral, we can ignore the contribution from S and just focus on the contribution from the asymptotic region. And in this asymptotic region, we can regard Tx mu nu as due to the incoming and outgoing object trajectories that are moving under each other's gravitational force. So here is a one-page summary of all the equations that we need. Okay, so this is the expression for the matter energy momentum tensor. This is the total energy momentum tensor. Okay, this is the equation for the E mu nu, and these are the equations for X. And here is the important point again: the boundary conditions. Okay. We put the boundary conditions on X, okay, so that dxi dt is specified at future infinity as tau goes to infinity, and dx prime beta is specified as tau goes to minus infinity. Okay, because those are the known object, known quantities, the incoming momentum and the outgoing momentum. Okay. And this is where the approach that we are going to that this approach differs from the earlier approach. Okay, where you start from some given initial data and then you evolve things simultaneously. Okay, you evolve the gravitational and matter equation simultaneously. So as I said, we solve these equations iteratively, starting with the leading solution where E mu is set equal to 0, and the x and x prime as just given by the free trajectories. And by iterating these equations, we get a series expansion in GM times omega, okay, possibly with logarithmic corrections. And if you want to get omega inverse and log omega terms, it's enough to do just one iteration. In fact, omega inverse comes just from the 0th order iteration, and log omega comes after one iteration. Okay. And omega squared log omega, which is needed for the F mu and the G mu calculations, we need one more iteration. And these basically generate some Feynman diagram like expansion, which you can evaluate. Okay, you still have to do some work, okay, to evaluate those Feynman diagram like integrals. Okay? But the procedure is more or less straightforward of how you go about doing this. Now, in the final 5 minutes, let me describe the relation to soft theorem. So I think I don't need to say in this audience what soft theorems are. Okay, they give the result for an amplitude with m soft gravitons in terms of amplitude without soft gravitons. So this is simplest in dimension larger than or equal to 5, where the S matrix is free from all infinite divergence, okay, and the soft theorems are well defined. Okay, so let me start from there, and then I'll come down to d equal to 4. But I should have said that the previous results that I described are all in d equal to 4. Okay, in d equal to 5, the structure is quite different. D equal to 5 onwards. But for soft theorem, we start with d 5 or larger. So the general structure of soft theorem is that the soft plus hard amplitude is given in terms of the hard amplitude by some matrix differential operator acting on the hard amplitude. Okay, so this involves orbital and spin angular momentum of external states. Okay, that's why it's a matrix as well as a differential operator. Now we take the classical limit by taking the hard particles to have mass that is larger than m, much larger than m Planck. Okay, they are heavy objects scattering. And we replace the orbital and spin angular momentum operators, okay, the SMs, which are operators, just by the classical spin and orbital angular momentum of the external states. Okay, so that's the procedure we use to describe the classical limit. Now, in this limit, it turns out that the soft theorem simplifies. Okay, in general, this SM is a complicated object. It doesn't factorize, okay, into product of individual soft particles. But in the classical limit, it does factorize into the product of the contribution from individual soft particles. Okay, so you can write it this way, where S alpha depends only on the quantum number of the alpha soft particle and those of the hard. And the idea now is that we will find a conditional probability for emitting m soft gravitons of certain quantum number for a given set of classical hard incoming and outgoing particles. So how do we do that? We take the mod square of this amplitude. Okay, so if you take the mod square of this amplitude, you get the mod a hard square. Okay. Then because you are taking all soft particles to have the same quantum number, okay, again, m soft with certain quantum number, we have mod s to the power 2m. This is a symmetry factor, 1 over m factorial. And then, of course, you have the phase space factor. Okay, 1 for each soft particle. So the phase space factor is raised to mth power. If you want soft particles emitted at different bins, okay, it will just contain more products of more terms like this. Okay, but it doesn't really matter. And now what we do is that we maximize this with respect to m. Okay, because you are trying to find what is the most likely number of soft particles that are emitted with a given quantum number. So you maximize this with respect to m, and that gives a classical number of soft gravitons with a given quantum number. And once you have got that, we can use it to determine the Fourier transform of the gravitational waveform of your phase. Because from the classical number of soft particles, you can find a total classical energy that is emitted in a given bin, and then that in turn gives you information of the gravitational waveform. So if in d larger than or equal to 5, this formula in fact works quite well, and it has been tested in many examples. And the soft factor turns out to give the gravitational waveform correctly without any additional phase. But in d equal to 4, there are two subtleties that you have to deal with. Okay, if you try to take the same formula and naively apply it to d equal to 4, The first subtlety comes because S alpha depends on the angular momentum of hard particles. This is of course true in all dimensions. But in d equal to 4, what happens is that the asymptotic angular momentum has this xi, and because of the long range gravitational force of other particles, the xi's have logarithmic corrections. Okay, so there is a term that is proportional to tau. Okay, tau is the proper time of the particle, but then there is a correction that is proportional to log tau. And because of this log tau factor, in this combination, there is a log tau left over. Okay, this term cancels, you can see, okay, because you anti-symmetrize. But this term gives a residual contribution proportional to log tau that doesn't cancel. So Gi mu nu actually diverges as tau goes to infinity. So it's not clear what the classical soft theorem means. And the way we resolve this is that we basically use the wavelength of the gravitational wave as an ad hoc infrared cutoff on tau. Basically, the idea is that if you are looking for gravitational waves of certain wavelength, then it should only depend on physics at scales that is smaller than that wavelength, okay, and it shouldn't depend on physics at scales larger than that wavelength. Okay, so he just put an ad hoc cutoff on log tau. The second subtlety comes because due to long range gravitational force, they have a Coulomb phase. Okay, so normally this e to the I omega r factor gets replaced by a logarithmic correction. This is the time delay that I mentioned. But once you have a log r, it's a question of it's log r over what. And we make the assumption that log r it's actually log r over the wavelength of the gravitational wave, with the intuition that the Coulomb drag on a wave of wavelength lambda should really act on it over a distance lambda to r. And with these two changes, okay, now you get the Fourier transform of the gravitational waveform, and you can Fourier transform it back, okay, and that's what gives the results that I quoted earlier. Okay, so the original argument that led to this form for F mu nu and B mu nu is this rule. Okay, and this is of course not rigorous, but this is much simpler than doing the actual calculation in the classical theory, okay, and it gives the right answer. So to summarize, basically in d equal to 4, the classical results from soft theorem should really be regarded as conjectures rather than derivations. Nevertheless, what we see is that the soft theorems do lead to correct conjectures. But I think what is more important is that the soft theorems teach us what questions might have universal answers, and universal answers that are independent of the details of the scattering process. For example, what soft theorem teaches us that we get universal results by asking for soft radiation for given initial and final hard particles. Okay, because that's what the soft theorem does, right? Given a hard amplitude, it gives a result for soft amplitude. Okay. So you have to specify the hard incoming and outgoing momentum, and only then you can hope to get some useful result. Okay. And that's what you also find from direct classical analysis. Okay, so this is the last slide, okay, for the future. Okay. So basically what the net upshot is that the power law decay in U, okay, comes from non-analytic function in frequency space. Okay. And non-analytic function in frequency space basically arise from infrared divergent terms, and hence they should be amenable to soft physics. Okay. The infrared divergent terms should be determinable by soft physics. Okay. So given this, we can ask the following questions. That first of all, can we develop a systematic procedure for computing all higher order terms in the large U expansion? Does the magical independence of the result on the final set massless particle data continue to hold, okay, at higher orders? And then finally, we can ask, do all such terms vanish for black hole margin? This certainly is of experimental relevance, because eventually we'll be able to see this in gravitational wave detectors. So with this, I'll stop. Thank you.
Thank you very much, Ashok. So we have about 4 to 5 minutes for questions. Andy?
How is the divergence, that log tau divergence in the angular momentum, how does that how is that consistent with angular momentum conservation? Do the C's have to sum to 0 or something?
Yeah. The total angular momentum is constant, indeed. Particles basically keep exchanging angular momentum, but if you calculate the total angular momentum of all the particles, that is 0. That the log tau coefficient vanishes for total angular momentum, because C's have definite expression in terms of the momentum of the other particles.
I see.
Because
Right.
these are long range gravitational force, right? So you know what these are in terms of the other particles.
So I think we had a more quantum version of some of these points in Alok's discussion.
Yeah.
And there was some relaxation on how the bonding news went to 0 at the boundaries of Scry, a slower fall off. And when I saw that, I interpreted that as, in the quantum world, well, maybe things are a little more delocalized and that affects that. But here your discussion is purely classical, right? Could you just comment on what's classical, what's,
Okay. Let me.
So a classical result, you wouldn't expect a slower fall off on the Bondi news, right? It was slower
So I think the classical result doesn't.
What?
Yeah, the classical result, right, goes as 1 over u, I think, which is consistent with everything that we know. It doesn't go as 1 over the faster than 1 over u. Okay, the delta term is missing. But in the quantum case, I think there is a log u term that is multiplying the leading term. Okay, which I don't know how to interpret. That you certainly don't see in the classical result.
Okay, but your log u's are not the same as his log omegas? Or
yeah, it is okay. There's one thing which is the soft theorem log u. Yes, and our log omegas is the same as their log omegas, but not. This is a special case. This is the classical limit already. Okay, the full quantum version had log omegas, but it's the same kind of log omega. The coefficient is different, but it's not that you have more divergent term. But when they tried to explain it from asymptotic symmetries, they had to change this coefficient, which seems very somewhat strange, because you certainly don't see this in the actual follow-up formula for E mu. Maybe if Alok is on, he can make some comments, but that's my understanding.
Thank you.
That's correct. So actually the classical symmetry analysis that Miguel explained is consistent with the fall-offs that Ashok has written here. But when we try to quantize the charge, the asymptotic conditions that we seem to require is more relaxed than you said, exactly what he said. And that is the origin of that is not clear to us. So the classical soft theorem Ashok did, we do understand it from conservation laws, and then the boundary conditions are exactly what he has written, which are the 1 by u. But maybe I can just make one statement that for super rotation charge to be well defined, we need a stronger follow-up than this even. Like we need the follow-up to be 1 by u to the power 1 plus delta. So with this follow-up, super rotation charges, at least to the extent we understand, are not well defined. So that's that issue to be already at classical level. There is something that has to be clarified.
Okay, we have the next talk in 1 more minute, so I suggest we move on and leave, any other questions for the break or maybe the discussion session later. So, Yuting?
Yes,
Are
hi.
you?
Yes,
Hi.
so now I'll try to share screen.
Sure.
So I think you need to let me share screen. Or
Okay. Just 1 second.
Just a second. You are a co-host, right? Oh, it dropped you out again. Just a second. I have made you co-host, or maybe you came in and out. Okay.
I can do it.
Yeah. Now you're.
Oh, yeah, okay, he's already.
thank you. 1 second. Okay, so is this, can everyone see this?
Yes.
Oh, okay, thank you very much. Okay, so then I'll just.
Okay, so
okay.
Yeah. Just let me just introduce you quickly. So next, we have Y-T.Huang from National Taiwan University with bulk locality on the celestial sphere. So go ahead, Y-T. Thanks.
Okay, thank you very much for the invitation. So I'd like to talk a little bit about some work we've done that was posted in this June. And this is with Chi-Ming Chang, Huang, Huang, and Wei Li. The last two are actually my students. So the motivation is that, of course, we've all heard from Simone that there's been a great deal of activity in the S-matrix bootstrap program, where we combine the constraints of unitarity, causality, and crossing to carve out the space of consistent gravity amplitudes. And for the details, we've heard from Simone's talk. But one of the important point is that it looks like it's really not enough. And I think a lot of these things has been discussed in the talk, but let me just point to, for example, just one example. So for example, just consider the 10-dimension supersymmetry. If you assume maximal supersymmetry, you can bound the coefficients essentially in terms of EFT, you can bound the coefficients for R4 in 10 dimensions. And so this is the bound that was mentioned in the talk. And as we've seen that you can compare this upper bound to the string theory value, and we see that there's a mismatch. And this mismatch is not really about the accuracy of the numerical method, because the numerical analysis is converging very well. So this is not a numerical issue. And so it looks like there's something missing. So what is missing from this list? Of course, one of the things is, as obvious, is that the high energy behavior, and in particular, it's not easy to get control over the high energy behavior for fixed angle scattering. But as we've heard over again in this workshop, the celestial sphere amplitude is basically engineered to have this nice property if it's well defined, if the integrals can be, if the Millen integrals can be done, then the celestial sphere amplitude should exist. Therefore, the question is that can we now build a bootstrap program based on the celestial sphere amplitude? So this is basically the motivation of our analysis. So basically, we will focus on the 4-point amplitude. And just schematically, in terms of notation, we'll be using this notation. So we'll be considering the T as our flat space amplitude, and then we're considering masses scattering, and we're performing a Millen integral transformation to get the celestial sphere amplitude. Now, so I won't talk a lot about the details of the various amplitudes. I just want to make some comments on the general properties. So from our point of view, we're not so interested, well, not interested, but we're not focusing on what is the theory that you have on the celestial sphere. Rather, we're actually more focusing on just what is the 4-point function and what properties do this 4-point function have. And one of the important properties is that there's actually 3 different functions on the equator. So this course, because of course, when we talk about 2-to-2 scattering, we have to determine which two particles are incoming and which 2 particles are outgoing. So so there's actually, at 4 points, there's 3 different kinematic regimes. And for each kinematic regime, you actually have a different function, and this will be really very important. And in fact, these 3 different functions are not directly analytically continued to each other. So these are 3 separate functions. To said in another way, we can do OPE expansion. For example, you can take this OPE expansion around here the function that the OP expansion coming from 0 plus is going to be very different than OP expansion coming from 0 minus, because these are just completely different functions. Now, of course, these regions are just corresponds to the 3 distinct physical regions. So in this talk, we will have from the 1, 2, 3, 4, the physical region is S is bigger than 0, UT is smaller than 0. For each region, we have one of the Mandel span to be positive, and the other will be negative. So we really have 3 different functions here. And of course, you can see that this is basically, if we plug in the parameterization, then this is the prescription we have for integrating the 3 functions in the different kinematic regime. Now, so the first thing that we want to establish is that we know that the flat space scattering amplitude. So we know one of the important aspects of the bootstrap was that we know that the non-analyticity of the amplitude at the flat space amplitude, and we know that the non-analyticity of the flat space amplitude, the residue and the discontinuity, and we have general properties associated with it. We can do partial wave expansion. The partial wave has positive expansion. So we want to see what is this statement, this image on the celestial sphere. So how do we see that the corresponding flat space amplitude has a pole, and this pole has a particular residue which has particular properties. Now, so just as always, we use a simple setup. So let's consider a massive scalar amplitude. So just to give us some idea of what would happen. Of course, this discussion has been studied by Lam and Xiao in 2017 in the context of 3D. And so for us, we're really focusing on the 4D story. So let's consider the S-channel kinematics, which means that we're on the celestial sphere and we're looking at when Z is between 1 and infinity here. So let's first focus on this function. For this function, you can directly integrate, and so this is just the final answer. And of course, it's very easy to track everything. So this is the S-channel contribution, this is the U-channel contribution, this is the T-channel contribution. Now, one of the immediate things that one sees is that the S-channel contribution has an imaginary part. These are real. And it's very simple to understand why. And when we're in the S-channel kinematics, on the complex omega plane, the S-channel poles sit on the real axes, whereas the T and U-channel poles sit on the imaginary axes. And that's why when you're evaluating the contribution from the S-channel pole, will give a contribution whose reality condition is going to be the opposite of the T and U channel. And so we see that there's a clean S-channel prediction contribution here. And indeed, if we consider just the imaginary part of this amplitude, then you can match it to basically just evaluating the residue of the S-channel exchange, and then project the residue onto the celestial sphere. Okay, so this is a very quick study of the scalar example, and so the claim is that this is actually universal. So the claim is that for any celestial sphere amplitude, the imaginary part will be given. So there's 3 different regimes, and so for each regime, the imaginary part will be given by the threshold of the physical channel. So there's not going to so in the S-channel regime, you're going to get S-channel pole. For T-channel regime, you're going to get T-channel pole, and U-channel regime, you're going to get U-channel poles. So and it's going to and basically the imaginary part is just going to be given by the residue. So first, I want to define I want to define the imaginary part of my celestial amplitude by defining it through a contour integral. So of course our original celestial sphere is defined along this contour, which is 0 to infinity here. So I'm going to assume that in general that the amplitude when we're extending away. So this is the W plane. So we know that generically this should be well behaved as omega goes to infinity in order for the integral to be well defined. But we're going to assume that this well behavedness at infinity has a small angle of analytic continuity, which this property is preserved. And of course, one can check with various amplitude. For example, the scalar amplitude is obvious. For string amplitudes there, which we'll actually focus on later on, this property is generic true. There's always a small angle of extension, which the infinity fall off is well behaved. So then, since by the way, so we're using the I-epsilon prescription where the poles are slightly shifted off the real imaginary axis and is shifted in this direction. So then, of course, this is the original definition of the celestial sphere amplitude with the I1 integral. If we consider the contour like this, if we consider this closed contour, then of course it's related to the negative of the integral in I2. So if we identify this fact, then we can easily define the imaginary part of the celestial sphere amplitude by considering instead this contour, where we integrate I2 prime is the image of I2, the symmetric image, since we're already assuming that the integral has well behaves at infinity for this small angle such that the I3 contribution will be vanishing. So that means the I3 prime will continue to vanish. Of course, then the I2 integral here is going to be related to the complex conjugate, the I2 prime. Sorry, the I2 prime integral here is related to minus the complex conjugate of I2. So we can combine these two combinations. Then we establish that the imaginary part of the celestial sphere amplitude is given by this contour, where the contour goes from I2 prime and I3 prime, but because I3 prime doesn't contribute, so it's really just I2 plus I2 prime, and which is the imaginary part. But at the same time, since this is a closed contour, so it just picks up these discontinuity. But importantly, the discontinuity or the singularity it picks up is only in the positive real S-axis, which is the S-channel thresholds, and therefore it's just given by the projection of the residue or discontinuity of the flat space amplitude projected onto the celestial sphere. So this is a simple way of proving analytically that statement. So of course, then we can just easily verify this. So let's just verify. So we know, for example, just consider string theory. So we have type 1 and type 2. So by here, for type 1 and type 2, I'm subtracting out the prefactor. So for the first thing I want to show you is that indeed you can see that there is a small angle extension in which the high energy behavior is well behaved even on the complex omega plane, not necessarily just on the real axis. So for example, so we're parameterizing S is omega squared, which is R exponential I theta. So we're looking at R goes to infinity and F theta is some complex extension. So generically, the amplitude will behave in this form. So the important point is that it's exponential R squared. So the question is, when is this function in front negative? If it's negative, then that infinity is well controlled. So basically, in general, this function is negative for some angle that is between 0 and sorry, this should be bigger and equal, 0 and some critical angle here. So for type 1, which is open string, generically the critical angle. So of course this is a function of z's, which is the parameter on the celestial sphere. So this angle goes from 0 to pi over 2. But important point is just that this theta c is generic. For generic values of z is non-zero. So there's a non-zero angular extension, which the amplitude falls off as exponentially. And for type 2 is generic. Sorry, I didn't write the value for type 2. So type 2 theta is just pi over 4. And it's actually z independent. So in the complex omega plane, so if I consider this in the complex omega plane, what that means is that for example, if you consider closed string, the type 2 theory, then along this region up to pi over 4 extension angle, the infinity is finite. Well, for type 1, depending on z, we can go all the way to pi over 2. The important point is just that the theta, this critical angle is not 0. So we can actually go on to the complex omega plane where we still can continue to disregard the counter integral at infinity. So since we can do that, then we expect this equation to hold. So we expect that we just take the imaginary part of that, the result of your projection onto the celestial sphere is going to be given by the residue of the flat space amplitude projected onto the celestial sphere. So we can directly check this numerically. So since we already know the residue of the flat space amplitude, it's very easy to just convert the residue of the flat space amplitude, change a variable and project it onto the celestial sphere. And then, then this will be a prediction. We're predicting that the imaginary part of the open string celestial sphere amplitude should be given by this formula. So this is the numerical analysis with specific. So here the evaluation is just literally just integrating from 0 to infinity, d omega omega beta. We just put in the open string amplitude here, and with the pose with the pose slightly shifted to I epsilon below the real axis, and then just do this integration numerically. And so you see that here this is the result. So these are the numerical result. And the different n here refers to, since this is really an infinite sum. So we have it, we just put a truncation here. And as you see that if we push higher and higher the truncation, this infinite sum is approximating the numerical value. So we play around with this for various z values. And so for example, we just pick some z, which is much greater than 1. Around, so we plot this region here and we see that it's a good match. We also plot it against z when it's close to 1, which means that it's close to one of the OPE limits. And indeed, again, once you this is a numerical value, so you see the numerical curve come here. And indeed, as we go to higher and higher truncation, this is faithfully reproducing the imaginary part of that result. You can do this, of course, for open closed string as well. And so you basically we see a similar result, both in the large, bigger than 1 region and close to 1 as well. So, okay, so maybe this is not so surprising, but importantly is that we know that the discontinuity and the residue has a positive expansion on a basis. So we've been talking about having a positive expansion that can be applicable to bootstrap using bootstrap methods. Here there is a positive expansion because we know that the flat space amplitude, the discontinuity and the residue has a positive expansion on the we were in 4 dimension. So this positive expansion will be on the Legendre polynomial. Therefore, this is a prediction. So the prediction is that if you consider the imaginary part of your celestial sphere amplitude in 3 different regimes, then each regime has a positive extension. This pi here is a positive value. So that has a positive expansion on these polynomials, which are nothing but the projection of your Legendre polynomial onto the celestial sphere. Now, of course, since we know what these polynomials are in flat space, so this here so far I've talked about massive scalars. We know what these polynomials are for spinning external states. So we can just immediately predict when the external states actually carry helicity, because in flat space we know that when you're on the threshold, the residue on the threshold is given by the Wigner D matrix. So then just following from the previous discussion, all we need to do is just project this Wigner D matrix onto the celestial sphere. And so this gives the prediction of the various expansion polynomials in the different kinematic regime. And these polynomials are essentially just the Jacobi polynomials. Okay, so and actually, what was interesting is that these projection of the residues in flat space onto the celestial sphere, you can actually identify with the Poincare partial waves that was introduced by Law and Zlotnikov. And of course, the Poincare partial waves is very similar. It was, so this is just a review of what they had. So they built this by considering, so you have the states on your celestial sphere, and of course you have a projection which projects to the spin J mass M intermediate state. And you can see that, of course, these functions should obviously satisfy the usual Poincare and Lorentz invariants, where these generators can be written as differential operators acting on the variables on the celestial sphere. And the important point is that there's two Casimir operator. One is defining the mass, and the other is defining the spin. So using these two, so finding the eigenfunctions associated with these Casimir operators then gives you the conformal partial waves. And so you can straightforwardly do that. And what they found was that the conformal partial waves are given by these Jacobi polynomials. And so, not surprising, these are exactly the same things that we're saying that the imaginary part has a positive expansion. So we've established essentially that the imaginary part of the celestial sphere amplitude now has a positive expansion. And that the statement is that that positive expansion is in terms of these conformal partial waves. So we have this formula here. So once we have this formula, then we can ask a lot of questions. Well, first of all, since this is really related to how we have control over the imaginary part of the amplitude, and of course we know that the imaginary part of the amplitude it can be feed into the dispersion relation. Then this immediately leads us to ask, what is the image of dispersion relations for the scattering amplitude on the celestial sphere? In other words, is there a dispersion relation on the celestial sphere? And furthermore, I think Monica will talk about this result in the next talk. We know that when we consider the celestial sphere amplitude as an analytic function of beta, we know at the negative integer values, the residue, there's going to be poles in beta, and these poles will be EFT coefficients. But from the scattering amplitude point of view, we know that these EFT coefficients are directly related to the imaginary part of the scattering amplitude, which then means that it's directly related to this part. And therefore, we might imagine that, okay, so this dispersion relation combined with this is now telling us that we're going to have the imaginary part of the celestial sphere amplitude, and then we evaluate the imaginary part at the residue where beta is set to minus negative integer, and we're going to get a non-trivial constraint. And this will be a constraint that we can impose on the 4-point function. And of course, furthermore, is that since we have a positive expansion, do we have a bootstrap problem now, finally? Now, of course, there's the elementary problem that we have in the very beginning, which is that we really have three different functions here. So indeed, even though we have so we have three different functions. So even though we have, for each function, it has a positive expansion in terms of a preferred expansion basis, it is unclear as if the three functions cannot be related to each other. Then we're just saying that there's three distinct functions, and the three distinct functions each have a positive expansion. There's no sense of crossing. We're not relating the sum expansion of one function to the another expansion in another function. So, and of course, this problem then feeds down to become an obstacle for trying to do anything that we try to aim to do here. So it looks like that we need to have a way. So even though the three functions you cannot directly analytic continue each other, but even though the three functions cannot be analytic, so this function here, actually, maybe this is even more useful. So let's just look at the scalar amplitude, and then you can see why. So this is what the scalar amplitude looks like in the 3 kinematic regime. And by looking at this, you can see that this is, I think it's pretty clear that there's no way of analytically continue from this function that such that it can match with this function. And so instead of trying to analytic continue relating these 3 functions, what we're going to do is instead to directly analytic continue this function to here, so that they have an image in here. In other words, we want to analytic continue the function which is previously defined in the physical regime to the unphysical regime. So we want to analytic continue to unphysical regime. So just as an example of that, using the scalar amplitude here. So for example, let's start with 1, 2, 3, 4, which is in the S channel regime. So this is in the physical regime. So which in the S regime, Z is between 1 and infinity. So now I'm going to continue this function to between the 2 unphysical regime. And the prescription is that when we go around 1, we have just going to pick up a phase here. When you go around infinity, it picks up a phase in this matter. And then we can get these 2 functions. Now, what is the prescription that determines this continuation? The prescription is that so where am I? Here. From the 1, 2, 3, 4 point of view, these two regions are, sorry, let me just use another color. So from 1, 2, 3, yes.
Just a quick reminder, but like 5 more minutes.
Okay, sure.
Okay.
So from the 1, 2, 3, 4 point, oops, sorry. So from the 1, 2, 3, 4 point of view, this is unphysical and this is unphysical. From 1, 3, 2, 4 point of view, this is unphysical. So the requirement is that the analytic continuation prescription must be such that if I start with this function, I continue here, it agrees with what this, if you start with this function and analytic continue here. So this is the prescription that we decided to fix this kind of analytic continuation. Then we can continue to the unphysical regime. So we can look, so once we continue to the unphysical regime, we can look at the imaginary part of, again, the original 1, 2, 3, 4, but now in the unphysical regime. And now we notice that the imaginary part is given by these 2 terms here. And these are nothing but the residue of the S and the T channel on the celestial sphere, where this is on the S and U channel. So so what this tells us is that the imaginary part of such analytic continued celestial sphere amplitude reflects the unphysical pose, corresponds to that region. So for this this region here, this was a U channel region. So actually, when this analytic continues here, this gives you the S and T channel factorization there. So remember, in the physical region, for the celestial sphere amplitude in the physical region, the imaginary part only receives contribution from the physical kinematic pole. If we add the analytic continuation of the other regions here, now we have information for all of the poles now. So therefore, what this tells you is that the dispersion relation that you have from the flat space, which tells us that the EFT coefficients are given by the imaginary part of the amplitude. Here, the imaginary part of the amplitude contains all factorization poles that contribute. Now we can directly imprint this on the celestial sphere, and therefore this is the formula that one has. So the statement is that consider the celestial sphere amplitude. You evaluate your beta at the -2n, which gives you the EFT coefficients here. This value will be related to the imaginary part of the celestial sphere amplitude in the physical region, as well as those from the unphysical region analytically continued here, and both evaluated at beta equals -2n. So this is the image of the dispersion relation that you would have in flat space. And you can check this image again, and I guess not surprisingly, indeed that this formula holds. So basically here we again use string theory to do this. Of course, It's obvious because we got this intuition from the scalar amplitude. So of course the scalar amplitude will satisfy this kind of dispersion relation. But now we can use string theory. So this what you do for string theory is first you evaluate the residue of the string theory celestial sphere amplitude on these. So this is at beta equals -10, for example. And then we use this prescription to compute the imaginary part of the celestial sphere amplitude involving the original amplitude and the analytic continued form. And then we can see that it's basically a direct match. So this is the same thing. This is we do it for both open string and closed string. Yeah, okay, so let me just wrap things up. So in summary, so basically that's, we see that the 4-point celestial sphere amplitude is given by we have three separate functions. And for each separate function, the claim is that the imaginary part has a positive expansion. And basically the positive expansion is in terms of the conformal, the Poincare partial waves. So even though these are three separate functions, but there's a well-defined way of analytic continuing each function from its original defining physical regime to the unphysical regime. And once you define this analytic extension, then you have a dispersion type relation, which is that the imaginary part of your original, so these are the same dispersion relation, the same the celestial sphere amplitude, combined with the celestial sphere amplitude, where you analytic continue from an unphysical region to your region. And then you evaluate a beta at -2, and then these things have to match with each other. And so this will be the dispersion relation that you have. And this is a reflection of the statement that the low energy expansion for your Wilson coefficients from an EFT point of view is related to the imaginary part of your amplitude. That statement whose image is basically takes this form. So of course, this is so at this point we're just giving these relations, and we can check these relations numerically. But to have control and really to translate this into a bootstrap problem will need further work. But I think this is an interesting direction, an interesting, promising direction to go into. So thank you very much.
Thank you very much, Yu-Ting, for the very nice talk. So we have plenty of time for questions. Ana Maria.
Hi, thanks for the nice talk. So I think you said this, but I missed it. So when you're deriving this relationship between the imaginary part of the celestial amplitude and this contour integral over the momentum space scattering amplitude, you're dropping the contribution from this piece of the contour you're calling I3, coming from essentially the large energy part of the momentum space amplitude at fixed scattering angle. And I think I missed about, like, first of all, I don't know how much is known about scattering amplitudes, like large energy behavior of scattering amplitudes at fixed scattering angle. And like, if you could repeat, like why you can drop that contribution.
Yeah, right. So of course so right now here we're working on the assumption that there's small. So first of all, for the celestial sphere to be well defined, it has to be well behaved when theta is equal to 0, which means that you're on the real line. So it has to be well behaved here. So we're basically assuming that it's not just well behaved at theta equals 0, it's well behaved actually at theta equals 0 and with small continuation onto the complex plane. So we're assuming that there's no not that I know of that there's any proof which this has to be true, but we're just assuming that. And the basis of our assumption is that we look at the amplitudes which have the celestial sphere prescription, which, for example, the scalar, the string theory amplitudes, and where it has vanishing contribution here. For each of those cases, we can extend onto the complex plane. So yeah, so that is our assumption. So in a sense, we're in a sense, you can say that we're chasing our tail, because because when we verify this imaginary part formula, we verify it against string amplitudes and such, where we know that there's such an extension.
I see. Thank
Yeah,
you.
but we don't have a general.
Would you expect it to be true in like
I would
quantum
expect it to be
theory or in
true.
general?
Yeah.
No,
Excuse me?
not just in gravity theories, like string theory.
I mean, certainly, certainly. I mean, well, I mean, well, first of all, for this is also true for open string. So it's not just for gravity, but yeah, but I would expect it for. I mean, so the statement is that I find it hard to believe that you have something which is well behaved at theta equals 0, but then just theta plus I epsilon is what ill behave. I think there's always some continuation where you can define that it's continue. Whereas, sorry, this is 0 plus I epsilon. So I would imagine that you can continue in such a way that it is still well behaved. But yeah, but that's an assumption.
Okay, thank you.
Andy, and then Monica.
Yeah, two things. The first is, so you're scattering what could be called Mellon conformal primaries, and they have the property that the scattering, there's a delta function as you use it, it's just a circle. But in the last couple of months, so there was an interesting paper by Fotopoulos, Seeberger, and Taylor, in which they did a shadow, and then also the work by Sharma doing a light transform. And then the 4-point function is extended over the whole Z. And these are perfectly legal states to scatter. We don't know which ones we should be scattering now. And then the amplitude is over the whole sphere. And you might hope to go, well, then you would have very different analyticity properties, right?
Yeah.
I would think you would have some, maybe it's meromorphic in Z. I don't really know. Have you thought about that, or?
Yeah, no. So yeah, so of course of course, but I haven't thought about it for those observable. But of course, so right now what we're doing here is that we're deriving these properties. We're just looking for what are the image of the analytic property which we know is true for flat space amplitude when you're doing this kind of projection onto the celestial sphere, and we're trying to find what exactly is that image. So I think it'll be interesting to, if we know that as we said, we know that the flat space amplitude has poles with residue, then for those, what is the image of this statement onto the celestial sphere when you're addressing it not with just these, but with also the shadow transform? What is the translation of that when you're using those external states? Yeah, so I think that'll be an interesting question. So right now we're just trying to do a translation of what because we want to. So I mean so the goal is that we want to know, we want to translate all of these properties which we know how to work with in flat space. So we want to translate this directly projected on the celestial sphere so that we can combine with the good high energy behavior. And so that is so I agree. Yeah, then it'll be interesting to see what does this translate to for those observables.
Yeah, very interesting. And my other question is, so you have this amazing final formula where maybe you could flip down to that. Yeah, so on the left-hand side, you've got the residues of the poles. And those are basically, for the 4-point function, those would be, we could think of those as the operator product coefficients on the celestial sphere, or we could think of them as the EFT 3-point couplings. And they have some positivity. And then on the right-hand side, these things, these are given by the massive states, right?
Right.
So, and those also have positivity properties.
Right. In a sense,
so you've got an equation relating 3-point to 2 points, and both sides are positive. That's
3 points to 2. What do you mean by 3 points to 2?
Well, so the right-hand side is coming from the massive states, right?
Right.
Oh, but that also contains 3-point couplings in it? It's
Yeah,
not just,
because it's a factorization. So it's how the massive states is contributing to factor that corresponds to the flat space amplitude factorizing. So it's really the product of 3-point.
right. Right, I see. Okay, wait, but so that's this contains the product of the 3-point functions and a sum over masses. And I guess the left-hand side is the 4-point functions. Right? Yeah, those poles are the 4-point terms in the EFT. So,
Right. So these are like contact terms in the EFT.
right.
And this is saying that this is basically the image. So this is basically the image of the bootstrap that we're doing. Is that the contact terms are given by a dispersion relation, the sum power, and whereas where instead of writing imaginary part, the imaginary part is given by some kind of 3-point factorization. And so that's basically this statement here.
So it's saying sort of 4-point interactions are determined by 3-point interactions as they are in 2-dimensional conformal field theory. Is that a fair? It's kind of a really direct.
But because this is really just picking up the imaginary part, so
it's just picking up the imaginary part.
Yeah, it's not saying that it cannot remove this imaginary part. No, this imaginary part is here. So yeah, so it's not that the entire, yeah, it's not the entire celestial sphere amplitude is related to, yeah. So I would say, I mean, yeah, from my point of view, it's really, this is really just the image of what we usually write down in flat space, which is that the contact term is given by some dispersion relation. Yes, this formula is really this.
I see.
Monica?
Right. So we just heard earlier this morning by Simone how you can, get more mileage if you think about the scattering of spinning particles.
Right.
But I mean, this is at fixed angles. So, and you showed some formulas, but what do you think about that?
Oh, yeah. So this is really, yeah. So this, the statement is that well, first of all, yes, this already includes spinning. So as you see, so previously when we started, we were discussing just about massive scalars, but then you can easily generalize where these actually includes the external states actually include spin. And when the external state includes spin, it's just that the polynomial expansion, you switch from the Legendre polynomial to these Jacobi polynomials. And indeed, the mileage that you have when you consider spinning, that mileage will exactly translate to here, to this form, through this formula, because as I mentioned, so this formula, so it corresponds to how many, yeah, it corresponds to which so I think the statement is that here we have beta equals -2n. So as you know that the n starts from 1, 2, 3, but actually it's not in this formula will not actually entirely work, because for example for n equals 1, because that corresponds to some s square, and now you actually depends on whether the twice subtraction can actually capture the s square. But what Simone was talking about was that if you have these spins, then these things are naturally captured then you can actually start to bound up, for example, n equals 1 as well. And so that mileage will also carry here. So basically the statement is that if you include external spins, if you consider external spins, then the mileage that you get from the dispersion, because the mileage is really about this dispersion relation, when does this equality hold? So the mileage that you get in when does this equality hold will directly translate to when does equality holds. So yeah, it will just direct translate. Sorry, probably I explained it in a roundabout way, but really the mileage that you get is in terms of how many subtractions you need to get this equality to hold, and that directly translate to when does this equality holds. In other words, so for which ends. So for which n? Yeah, so that's the same.
Thanks.
More questions? There's a question in the chat by Igor Mol. Igor, I don't know if you want to do it out loud or
non-supersymmetric confining QFTs.
yeah, I think it was
I guess-
related to to the first question. I think it was related.
Well, I mean, I think if it's confining, then we're not talking about these are then you have confinement, so you have massive states, right? So we're really just talking about massless scattering. Yeah, so this is really strictly massless.
Okay, good. More questions? No.